You know, when you see a self-driving car navigate a busy street, or when your email just knows what's spam, have you ever wondered how it does that? It's all about making smart guesses with incomplete information. And today, we're going to pull back the curtain on how machines learn to reason with uncertainty. So that's the big question, right? How do we get machines to think about uncertainty? You and I, we have this gut feeling. We see dark clouds, we grab an umbrella. It's intuitive. But how do you teach a machine that same kind of predictive power? How does it learn to connect the dots between cause and effect to make its way through a world that's never 100% predictable? Well, before an AI can predict anything, it needs a map, but not a super detailed one. It's more like a simplified model of the world. Look at this little robot building a blocky Earth. That's kind of what we're talking about. AI models can't capture every single tiny detail. They'd be totally overwhelmed. So instead, they focus on what really matters, the crucial relationships between things. And this whole idea brings us to what's known as the prediction problem. See, to make any kind of forecast or diagnosis, we need a way to officially represent these relationships and all the uncertainty that comes with them. So you might be asking, why do we even need these models? Well, think about your own life. You hear a weird noise in your car. Is it the engine or something else? You're launching a marketing campaign at work. Is it actually going to boost sales? These are exactly the kinds of questions that probabilistic models help us answer. They are the secret ingredient, the hidden engine behind, well, pretty much everything, from high-stakes finance and robotics to the AI characters in your favorite video games. Okay, so how do we build one? Well, the most obvious way leads us straight to the villain of our story today. An impossibly large table. The idea seems so simple at first, right? Why not just list out every single possible thing that could happen in the world and then just slap a probability on each one? This massive list, this giant ledger, is called a full joint distribution table. And you know, for a really, really simple world, it works perfectly fine. Let's say we only care about two things, temperature and weather. You can list out all four combos, hot and sunny, hot and rainy, you get the idea, and give each one a probability. See how they all add up to 1? That's our whole universe of possibilities. Sounds easy, doesn't it? Well, yeah, not so fast. As the source material puts it so well, this whole approach just completely falls apart almost immediately. The second you add more than just a couple of variables, this table blows up into something monstrous, something you just can't manage. But how huge are we talking? Well, if you have n variables that can be true or false, the number of rows you need is 2 to the power of n. And that's exponential growth. It's a killer. With just 10 variables, you're already over 1,000 rows. Okay, maybe manageable, but with 30 variables, you're talking over 1 billion rows. It's computationally impossible. No way! So, okay, that's a dead end. The brute force method is out. But this is where it gets good. A really beautiful, almost simple idea comes in and saves the day. This is the aha moment that really makes modern probabilistic AI possible. And the hero of our story has a fancy name, conditional independence. Sounds complicated, I know, but the idea behind it is incredibly simple. All it really means is that sometimes knowing one thing makes another thing totally irrelevant. Okay, so look at this. The formal math on the left, yeah, it can look a little scary, but don't worry about it because the picture on the right makes it all make sense. All that math is really saying is that the probability of X happening, once you already know that Z is true, doesn't change one bit, even if you learn about Y. Let's make this real. So, let's go back to our umbrella. Your decision to grab an umbrella. What does it depend on? The rain, obviously. Now, rain also affects traffic, right? But here's the key question. Does the traffic affect your umbrella decision? Of course not. Once you know the most important fact, it's raining, what the traffic is doing becomes completely and utterly irrelevant to whether or not you need that umbrella. That right there, that's conditional independence. And this one single, elegant insight lets us build an amazing tool for modeling the world, a way to literally draw a map of uncertainty. And that tool is called a Bayes net. And it's just what the source says. It's a technique for taking that giant, impossible table we talked about and smashing it into tiny, simple, local pieces. Instead of tracking every single possible combination of things, we just focus on direct influences, cause and effect. Let's actually see how this works. We can just draw it out. So we start with a node for a cause. Let's say rain. Then we draw arrows to things it directly causes. So rain can cause traffic, right? Boom, there's an arrow. Rain also makes you grab an umbrella, so another arrow. And just like that, we've built a tiny Bayes net. And notice what's missing. There's no arrow from traffic to umbrella, because one doesn't directly cause the other. And if you just keep applying that simple logic over and over, you can build these really cool intuitive maps of how everything interacts. Now, the technical term for this is a directed acyclic graph, which is just a super fancy way of saying it's a map with one-way streets and you can't go in circles. It's literally a map of what influences what. So here's the takeaway. A Bayes net is made of two key things. First, you've got the topology, that's the graph itself, the drawing with the nodes and arrows that shows you the structure. And second, you have the local conditional probabilities. Those are just the numbers that tell you how strong each of those connections are. You know, like if it's raining, there's a 70% chance I'm bringing my umbrella. So what does all this elegance get us? Why did we go through all this? Well, this is the payoff. This is our hero's big victory. Let's go back to that villain, the impossible table. Storing that thing took an amount of memory that grew exponentially. It just runs away from you. But with a Bayes net, the storage you need only grows linearly. That is the difference between an impossible problem and a problem we can actually solve. It's an absolute game changer. The payoff here is it's huge. You save a ton of space and computing power. It's way easier for a machine to learn these simple little connections from data than it is to try and figure out that giant table. And maybe the best part for us, for people, is that the graph itself just makes sense. It represents knowledge in a way that we can actually look at and understand. So the next time you interact with a piece of really smart tech, maybe a medical tool making a diagnosis, or your spam filter working its magic, or a recommendation engine that just gets you, take a second. Think about the elegant map that might be running things behind the scenes. Because a lot of the time, the secret engine behind modern AI isn't some scary, unknowable black box. It's one of these beautiful, intuitive maps of our very uncertain world.